In 1980, an American P-3 Orion surveillance aircraft drops a sonobuoy into the North Atlantic. The acoustic technicians on board pick up a Soviet submarine. Standard procedure. They have tracked Soviet boats thousands of times before. But this time, the contact accelerates, and it keeps accelerating. The needle climbs past 30 knots, past 35, past 40. The American operators stare at their instruments in disbelief. No submarine moves that fast. No submarine can move that fast. And then, the contact vanishes. At 41 knots, the Soviet submarine simply outruns the tracking equipment. The Americans have just encountered something that should not exist. The submarine they lost that day was a Project 705 Lira. NATO called it the ALFA class. And its existence triggered the most serious crisis in American anti-submarine warfare since the Soviet Union first developed nuclear submarines. Consider what the United States Navy faced. Their primary weapon against enemy submarines was the Mark 48 Torpedo, top speed of approximately 55 knots. But the ALFA could sustain 41 knots indefinitely, and at those speeds, the submarine could execute radical turns that no torpedo guidance system could follow. Simple geometry became a nightmare. If an ALFA detected a torpedo launch and accelerated while turning away, the torpedo exhausted its fuel before it could close the distance. The entire American torpedo arsenal had suddenly become ineffective against one class of Soviet submarine. But speed was only part of what made the ALFA impossible. The Soviets had built this submarine from titanium, the entire pressure hull, every frame, every plate. The first and only submarine class in history constructed entirely from this metal. And the reactor at its heart operated on principles so dangerous that many Soviet engineers believed the design was insane. This is the story of the ALFA class, a submarine so extreme that it broke the rules of what naval engineering could achieve, and a submarine so dangerous that the men who sailed on it knew they were operating the most terrifying machine afloat. The origins of Project 705 trace back to 1957 and a Soviet naval architect named Mikhail Georgievich Rusanov. Rusanov was not interested in building better versions of existing submarines. He wanted to build something that would make all existing submarines obsolete. His vision was radical. A small, heavily automated attack submarine with a crew of fewer than 40 men that could outrun any weapon designed to kill it. At the time, this seemed impossible. Nuclear submarines required large crews. The American Skipjack class carried 93 men. The Soviet November class needed over 100. These boats were complex machines requiring constant human attention. Reactors needed monitoring. Weapons systems needed operators. Damage control required bodies. Rusanov proposed cutting crew requirements by 2/3. His solution was automation on a scale never attempted in submarine design. The ALFA would feature a central combat information system that handled tasks requiring dozens of sailors on conventional boats. Navigation calculations, weapons targeting and launch sequences, damage assessment and response recommendations, all managed by computers that were revolutionary for their time. The crew would supervise the systems. The machines would do the work. The Soviet Navy's leadership was skeptical. Automation failed. Computers crashed. When something went wrong, 300 meters beneath the surface, you needed men who could respond. But Rusanov had answers: redundant systems, manual backups, and a submarine so fast that it could escape any situation before the crew needed to intervene. The Central Committee approved Project 705 inches 1,960, but automation alone could not deliver the performance Rusanov envisioned. For that, he needed materials and propulsion systems that did not yet exist. The pressure hull came first. Steel has fundamental limits. To dive deep, you need thick steel plates. Thick steel means heavy weight. Heavy weight requires more power to move at speed. More power requires larger reactors. Larger reactors require larger hulls. Larger hulls require more steel. The cycle feeds itself, producing submarines that grow bigger and heavier with each generation. Titanium breaks this cycle. Pound for pound, titanium is stronger than steel. Its strength-to-weight ratio is substantially higher. A titanium hull can dive deeper than a steel hull of equivalent weight. Or it can achieve the same depth with much less weight, freeing that weight savings for other systems. Rusanov chose the second path. He would build a small, lightweight submarine that could go deep and go fast. The technical challenges were immense. Titanium is notoriously difficult to weld. The metal reacts with oxygen at welding temperatures, creating brittle joints that crack under pressure. The contaminated welds look fine during inspection, but under the stress of deep diving, they fail. One bad weld means a dead submarine. The solution was to weld in a pure argon atmosphere. No oxygen, no contamination. But this meant constructing entire sections of the Sudamek shipyard in Leningrad as sealed chambers filled with argon gas. Workers entered through airlocks wearing breathing apparatus. Every weld took place in an artificial atmosphere maintained by industrial gas systems. Quality control required X-ray inspection of every joint. A single flaw meant cutting out the section and starting over. The cost was staggering. The titanium itself was expensive. The specialized welding facilities added enormous overhead. The training required for workers was measured in years, not months. A single ALFA hull required more money than an entire conventional submarine built from steel. The Soviets built the facilities. They trained the welders. They developed new inspection techniques. They solved problems that Western engineers did not believe had solutions. By the late 1960s, the first titanium hull sections were taking shape in Leningrad. But the reactor was the true revolution. And the true danger. Conventional nuclear submarines use pressurized water reactors. Water circulates through the reactor core, absorbs heat from nuclear fission, and transfers that heat to steam generators. The steam drives turbines. The turbines turn reduction gears. The gears spin the propeller shaft. It is a proven system, well understood, with decades of operational experience. American submarines have used pressurized water reactors since the Nautilus first went to sea in 1954. Rusanov rejected this approach. Pressurized water reactors require large, heavy pressure vessels. The water must be kept under intense pressure to prevent it from boiling inside the reactor core. This means thick-walled containment systems rated for extreme conditions. All that metal adds weight. All that weight reduces speed. Rusanov wanted something lighter, something more compact, something that could deliver more power from less space. His answer was liquid metal cooling. Instead of water, the ALFA's reactor would use a eutectic alloy of lead and bismuth as the primary coolant. This metal mixture has remarkable properties. It absorbs heat more efficiently than water. It does not need to be pressurized because its boiling point is far above reactor operating temperatures. It allows reactor cores to be smaller and more powerful than water-cooled designs of equivalent output. The trade-off was terrifying. Lead-bismuth alloy melts at 257 degrees Fahrenheit. Below that temperature, it is solid metal. If the coolant solidifies inside the reactor, it blocks the circulation paths. The primary loop becomes a solid mass of frozen metal and nuclear fuel. It cannot be restarted. It cannot be repaired. It cannot be refueled. The reactor is destroyed, and the submarine must be scrapped. This meant the ALFA's reactor could never fully shut down. From the moment the reactor first went critical to the moment the submarine was decommissioned, the coolant had to remain liquid. The reactor had to keep producing enough heat to prevent the alloy from freezing, even in port, even during maintenance. Even when the crew was ashore on leave, the reactor stayed hot. Auxiliary heating systems provided backup if the reactor's own heat output dropped too low. Electric heaters wrapped around the primary loop piping could maintain temperature during low-power conditions. But these systems required constant monitoring. They required reliable shore power connections. They required technicians who understood what they were looking at and could respond to problems before they became catastrophic. A failure during a port visit, a power outage that interrupted the heating systems, a technician who misread a gauge, any of these could destroy the reactor in hours. The first ALFA, designated K-64, launched in 1969 from the Sudamek shipyard. Sea trials began in 1971. The reports that filtered back to Soviet Naval Command were almost unbelievable. During speed runs in the Barents Sea, K-64 achieved 41 knots submerged. Some reports from her crew suggest she touched 43 knots under optimal conditions, with a clean hull and favorable water temperature. For comparison, the American Los Angeles-class submarines entering service at the same time could manage approximately 32 knots at maximum power. The ALFA was nearly 10 knots faster than the best the United States Navy could build. In a stern chase, no American submarine could catch her. Acceleration was equally impressive. From a standing start, the ALFA could reach full speed in approximately 60 seconds. The lag time between ordering flank speed and achieving it was measured in heartbeats. Conventional submarines took several minutes to build from cruising speed to maximum velocity. Their reactors needed time to increase power output. Their turbines needed time to spin up. The ALFA's compact, powerful reactor and lightweight hull allowed performance that bordered on impossible. Diving depth reached at least 1,300 feet. Some estimates, based on hull stress calculations, put maximum operating depth closer to 2,000 feet in emergency conditions. The American Mark 48 torpedo of that era had a maximum engagement depth of approximately 1,200 feet. An ALFA, operating at its design limits, could descend beyond the reach of American weapons and simply wait while the torpedo swam uselessly overhead. The United States Navy had a problem that could not be easily solved. American anti-submarine warfare doctrine assumed that torpedoes could catch their targets. Speed differentials of 10 to 15 knots between torpedo and submarine gave the weapon time to maneuver, to correct course, to close for the kill. An enemy submarine trying to evade would exhaust its options before the torpedo exhausted its fuel. But the ALFA changed the mathematics. A submarine that could nearly match torpedo speed and exceed torpedo maneuverability was functionally immune to the standard American response. The response came in two forms. First, an immediate acceleration of the Mark 48 ADCAP program. ADCAP stood for Advanced Capability. The new torpedo variant would be faster than the standard Mark 48. Its guidance systems would be improved to track targets executing radical evasive maneuvers at high speed. Its range would be extended so it could engage from further distances before the target could detect the launch. The ALFA threat pushed development timelines forward by years. Budgets increased. Engineers worked overtime. The Navy needed a weapon that could kill something it had never imagined fighting. Second, the Navy began developing new tactical approaches. If you could not outrun an ALFA, perhaps you could ambush one. Position attack submarines along likely patrol routes. Wait in silence with systems powered down and crew at minimum noise conditions. Fire before the ALFA knew you were there. The problem was that the ALFA was surprisingly quiet at low speeds despite its exotic reactor. And at high speeds, it could outrun any response you mounted. Finding an ALFA was difficult. Surprising one was nearly impossible. Killing one was something no American submarine captain was confident he could accomplish. The situation within the ALFA program itself was more complicated than Western intelligence understood at the time. K-64, the first of the class, suffered a serious reactor casualty in 1972. The liquid metal coolant leaked from the primary loop into the reactor compartment. Lead-bismuth alloy at operating temperature is highly radioactive. Neutron bombardment in the reactor core activates the metals, creating dangerous isotopes. Polonium-210 forms as a decay product of bismuth-210. This is one of the most toxic substances known to science. Microgram quantities can kill a human being. Contamination spread through the engineering spaces of K-64. The damage was serious enough that the submarine was withdrawn from frontline service. Soviet engineers studied the failure in detail. They made modifications to the primary loop design. They improved quality control on the piping welds. But the fundamental danger of the liquid metal system could not be engineered away. The reactor was inherently more dangerous than a conventional pressurized water design. That danger was the price of performance. Crew recruitment became a problem that the Soviet Navy never fully solved. Word spread through the submarine fleet about the boats that could never shut down their reactors, about the automation systems that sometimes malfunctioned in ways that conventional systems did not, about the assignment where your dose rate was higher than on any other boat in the fleet. Veterans avoided ALFA duty when they could. Command positions sometimes went unfilled for months, while personnel officers searched for qualified volunteers. The men who did serve on these submarines understood both the capability and the danger. They were operating something unprecedented, the fastest submarines in the world, the deepest diving, the most automated. For ambitious young officers, it was the frontier of naval engineering. For others, it was an assignment you endured rather than embraced. 7 ALFAs entered service between 1971 and 1981. K-64 was the troubled prototype that proved the concept but never fully recovered from her reactor problems. K-123 followed in 1978. Then K-316, K-373, K-432, K-493, and K-463 completed the class over the following years. But on May 8, 1982, the danger at the heart of the ALFA design announced itself in a way that could not be contained or concealed. K-123 is running at depth in the North Atlantic. Her liquid metal reactor is operating normally. The lead-bismuth coolant circulates through the primary loop at approximately 900 degrees Fahrenheit, absorbing heat from the reactor core and transferring it to the secondary steam system. Temperatures are stable, pressure is within normal parameters. The crew of 32 men is at routine watch stations. Then an instrument reading changes in the control room. Radiation levels in the reactor compartment begin to rise. The primary loop is leaking somewhere in the system. Radioactive coolant is escaping into spaces where it should not be. Emergency procedures activate immediately. The crew isolates affected compartments, sealing hatches to prevent contamination from spreading. But on a submarine, isolation is imperfect. Air recirculation systems connect all spaces. Contamination migrates through ventilation ducts, through gaps in seals, through the simple movement of men responding to the emergency. K-123 surfaces. The fastest submarine in the world cannot outrun what is happening inside her own hull. She makes for home, heading east toward the Kola Peninsula at a fraction of her potential speed. The emergency has been reported. Assistance is on the way. But the damage is already done. The investigation that followed revealed a failure in the primary coolant loop piping. A weld joint had developed a crack under the stress of repeated thermal cycling. Every time the reactor changed power levels, the piping expanded and contracted slightly. Over thousands of cycles, the cumulative stress exceeded the metal's tolerance. The crack propagated. The leak began. The exact cause remained classified for decades. What became immediately clear was the damage. K-123's reactor compartment was so heavily contaminated with radioactive lead-bismuth residue that conventional decontamination was impossible. Workers could not enter the space for extended periods. Equipment could not be safely handled. The submarine that could outrun any torpedo was crippled by what had leaked from her own reactor. The decision was made to cut the reactor compartment out of the hull entirely and replace it with a new section. This was not repair. This was rebuilding the submarine from the middle outward. The process required specialized facilities, radiation-hardened tooling, and workers willing to accept elevated dose rates for extended periods. It took 9 years. K-123 returned to service in 1992, operating until the class was retired in 1995. But those 9 years represented an investment of resources that few other submarines could justify. Throughout the 1970s and 1980s, the ALFA class experienced reactor problems that never became public knowledge until after the Soviet Union collapsed. 2 boats suffered the ultimate nightmare of liquid metal cooling, coolant solidification. The auxiliary heating systems failed or were improperly managed during port periods. Shore power connections dropped at the wrong moment. Technicians who should have been monitoring temperature gauges were assigned elsewhere. The lead-bismuth alloy froze in the primary loops. The reactors died. These submarines were towed back to port with dead reactors, their engineering spaces filled with hundreds of tons of solid metal that could never be liquefied again. The fission products inside the frozen cores would remain radioactive for centuries. The submarines were useless, too dangerous to enter, too expensive to dispose of properly. They joined the growing collection of nuclear waste that the Soviet Navy was accumulating in remote Arctic facilities. The economics of the ALFA compounded these operational problems. Each submarine cost roughly 5 times as much as a conventional Victor III class attack boat. The titanium hulls required the specialized shipyard facilities in Leningrad that existed nowhere else in the Soviet Union. The liquid metal reactors required constant shore support to keep the coolant from freezing when the boats were not at sea. The automation systems required technicians trained on equipment that existed on no other class in the fleet. By the late 1980s, the Soviet Navy was spending enormous resources to keep 6 or 7 submarines operational. The boats performed magnificently when they worked. Speed runs still exceeded 40 knots. Dive depth still reached beyond anything American submarines could match, but they demanded a level of support infrastructure and constant attention that the Soviet economy increasingly could not provide. The men who served on these submarines until the end understood what they had been part of. They had operated the most extreme submarines ever built, reactors that could not be shut down, hulls built from metal that resisted every conventional construction technique, automation that replaced the manpower conventional submarines required, speed that nothing else in the ocean could match. The last ALFA was decommissioned in 1996. The Russian Navy, successor to the Soviet fleet, could no longer afford to maintain ships that demanded so much and delivered so little operational availability. The titanium hulls, worth fortunes as scrap metal, were cut up at naval shipyards. The dead reactors, frozen or contaminated or simply worn out, were stored at facilities in the Russian Arctic alongside the accumulated nuclear waste of 5 decades of submarine operations. What remains is the legacy. The ALFA proved that liquid metal reactors could power submarines. The engineering was dangerous. The operational demands were extreme. The cost in equipment and human exposure was significant, but it worked. The technology produced performance that pressurized water reactors could not match. Russian naval engineers continued to explore liquid metal cooling for specialized applications in the decades that followed. The ALFA forced the United States Navy to confront a future where existing torpedoes might not be adequate. The Mark 48 ADCAP emerged directly from the ALFA crisis, entering service with capabilities specifically designed to engage targets moving faster than anything previous torpedoes had been designed to catch. Subsequent American torpedo development continued to emphasize speed and maneuverability, specifically because of what the Soviets had demonstrated was possible. The ALFA showed what titanium construction could achieve. The weight savings translated directly to performance. The depth capability exceeded what steel hulls could reach. No other nation has built an all-titanium submarine since the last ALFA was completed. The costs are prohibitive. The technical challenges remain immense, but the path has been proven. If economics or strategic necessity ever justify the investment, the Russians demonstrated it can be done. Perhaps most importantly, the ALFA reminded both sides of the Cold War that their opponent was capable of the unexpected. American naval intelligence tracked Soviet submarine development closely. They monitored launches, they recorded sea trials, they gathered acoustic signatures whenever they could, but the ALFA still surprised them. The performance exceeded what their analysis predicted. The engineering solved problems that Western experts considered unsolvable. The Soviets had built something that changed what seemed possible. 7 submarines, approximately 32 men in each crew, a design that pushed beyond every accepted limit of submarine engineering. Reactors that demanded constant attention, that could never be allowed to cool, that threatened catastrophe with every unexpected shutdown. The men who sailed on ALFAs knew they were doing something unprecedented. They operated the fastest submarines ever built. They dove deeper than almost any other combat submarine in history. And they lived with a reactor that demanded vigilance every hour of every day. Whether the boat was at sea or tied to a pier, the reactor never rested. Neither could they. The ALFA class was not a practical weapon system in the end. Too expensive to build, too demanding to operate, too dependent on infrastructure that could not be replicated at scale. But it was a demonstration of what was possible when engineers were given permission to ignore conventional limits, when speed mattered more than cost, when performance justified any risk. The Cold War ended before either side had to discover what would happen when an Alpha met an American submarine in actual combat. The missiles were never launched. The torpedoes were never fired in anger. The confrontations beneath the Arctic ice remained games of cat and mouse, not shooting wars. But somewhere in the North Atlantic, in the early 1980s, American submarine captains tracked contacts that accelerated past 40 knots and vanished into the deep. They wrote reports that filtered up through the chain of command. They described encounters with something that changed what they believed was possible in submarine warfare. The Alpha was the submarine that should not have existed, built from impossible metal, powered by a reactor that could never sleep, crewed by men who understood they were operating the most dangerous machine in the Soviet fleet. For 15 years, it existed anyway, and nothing that encountered it was ever quite the same.